Hello, everyone. I hope you can hear me well. I hope you can see me well. My name is Ilya Jackson, a postdoctoral associate at MIT Center for Transportation and Logistics. And today I'm privileged to present you this study, Deep Reinforcement Learning for Supply Chain Synchronization. The outline of the presentation corresponds to the structure of the paper. In the past, supply chain management was mainly focused on management of operations and material flows. However, in recent years, the focus has shifted to the management of information and data flows. The widely known bullwhip effect, also known as the Forester's effect, and information amplification is a consequence of the information miscoordination in supply chains. Bullwhip effect is the phenomenon experienced in practice, signifying the propagation and amplification of orders as they pass upstream in a supply chain pipeline. The bullwhip effect is a significant problem for supply chain managers because it eventually causes over and under production cycles, akin to Kondratiev cycles in economics. So the demand-supply synchronization as the potential solution to this problem. And it's worth mentioning that synchronization is a novel and quite a vague term. And in this study, we define synchronization in a very narrow sense, namely as the dynamic, adaptive demand-supply synchronization, demand-supply matching. In order to achieve this objective, production, scheduling, inventory control, and transportation plans must be synchronized among a multitude of individual supply chain participants that may frequently spread across the globe. Since inventory level is a difference between inbound and outbound material flows, automated inventory control is a pivot of supply chain synchronization and the main focus of our study. What really served as the inspiration for this work is the ability of intelligent systems based on deep reinforcement learning to master computer games at a level superior or frequently significantly superior to that of a professional human players. All jokes aside, you may remember how many skeptics undervalued the astonishing success of AlphaZero in mastering such classic board games as shogi, chess, and Go. However, skeptics were pointing out the relative simplicity of rules and determinism of games. However, it appears that deep reinforcement learning is also capable of mastering video games that partially capture and reflect the complexity of real-world decision-making. Notable examples include Dota 2, StarCraft 2, and Minecraft, and Atari games, for sure. The complexity of the mentioned games can be characterized by long-term planning horizons, partial observability, imperfect and frequently incomplete information, and high dimensionality of both actions and state spaces. So, Markov decision process, or simply MDP, is a powerful, nevertheless flexible framework for reinforcement learning. In a nutshell, there are two core elements. The first one is the environment, or simulation, or virtual world. Environment. The second core element is a reinforcement learning agent. yeah, roughly speaking, intelligent system. So the agent can observe environmental states, state S, and perform action A out of the set of available actions. Based on performed action for a given state, the agent receives a reward, which is the function of action and state. And the goal of the reinforcement learning is to come up with the policy P that will map states to actions in such a way that the cumulative reward over the time horizon is maximized. So, supply chain environment. We consider a quite simple single product supply chain model. There are many sites, M sites to be specific, also known as tires. Yeah, I stands for inventory on hand. Q corresponds to the accepted reorder quantity, and Q hat, this one, is the requested reorder quantity. Yeah, L stands for replenishment lead time between stages, and demand D is a discrete random variable under Poisson distribution. And net profit, denoted as NP, equals to sales revenue minus procurement cost, penalty costs, and all other costs. Yeah, roughly speaking, net profit is the difference between the income and expenses. Yeah, and subject of maximization over the time horizon. So we used proximal policy optimization, or simply PPO, the policy gradient algorithm invented by OpenAI in 2017. By the way, 5 years passed, but it's still the state of the art. The algorithm is implemented in parallel using the array framework. The framework performs actor-based computation orchestrated by a single dynamic execution engine, which is extremely convenient for cloud implementations or cluster-based implementations. Besides that, Ray is distinguished by a distributed scheduler and fault-tolerant storage framework. The numeric experiment is conducted in a fully reproducible manner using Google Collaboratory, a hosted version of Jupyter Notebooks. You can see the hardware specifications here. From my side, I just want to highlight that anyone, absolutely anyone, can get 4.1 teraflops absolutely free of charge, which is a lot, just a lot. So finally, experiments. The first numeric experiment is conducted with a 4-stage supply chain. The second numeric experiment is performed with a 5-stage supply chain using more challenging environmental settings. In both cases, the proposed approach is compared with the base stock policy. Base stock policy is a well-known approach in classic operations research and inventory control theory. In the first experiment, the PPO agent, I will even show that. In the first experiment, the PPO agent could derive a policy that led to an average reward of 425.6 abstract monetary units, which is 2.7% higher, well, basically a small margin, but at the same time, having a smaller standard deviation of 19.4. In the more challenging case, the PPO agent managed to adopt and find the policy that entails a positive net profit in the specified environmental setup. At the same time, the policy based on base stock didn't lead to a profitable outcome. The figure illustrates the inventory dynamics for 2 weeks at all the stages under the control. It's quite interesting that the PPO agent derived the control rule that entails notable fluctuations for a retailer and a wholesaler. It's not a disaster and rather shows the agent's ability to adapt and adjust. So, to conclude, proximal policy optimization algorithm can perform adaptive control in complex supply chains and clearly has the potential to solve supply chain synchronization problems. The conducted numerical experiments demonstrated the capability to outcompete the base stock policy. From the industrial applicability point of view, the assumption of end-to-end visibility may be considered unrealistic in many real-world settings, especially taking into account the current level of digitalization. And we may conclude that the adoption of the fully-fledged supply chain digital twin can be considered a mandatory infrastructural condition. But I hope to believe that shocks and disruptions amid the COVID-19 pandemic, along with post-pandemic recoveries, can become a catalyst for necessary changes in information transparency and global coordination. Theoretically speaking, it would be nice if one company or entity, let's call it singleton, can take over the whole supply chain from raw material to end consumer. Yeah, and Tesla has been vocal in its rejection of the traditional franchise dealer sales models, preferring instead of selling directly to their end customers, which may be considered as a first step in the right direction. Historically, actually, there is no wonder. Yeah, historically, the automobile industry has pioneered an impressive number of supply chain innovations. For example, Ford's assembly line, Toyota's lean manufacturing, just-in-time, or Kanban originally. So let's wish Elon Musk all the best in his ventures. So, and in short, is the proposed solution ready to deploy? No, absolutely not. Yeah. Is it perfect? Also no. But does it have potential? Absolutely. And I hope that with this presentation, we could demonstrate that. So with this, I end my talk. Thank you for attention. And as a small side note, I just want to highlight that all the experiments are conducted in fully reproducible manner and available in GitHub, in our GitHub, so anyone can access the source code, play around with it, tweak parameters, and maybe you will come up with a solution that I couldn't discover.